Are we? Hello? All right. Hello, everybody. My name is Michael Kamen. Today we're going to be doing an introduction to semiconductor manufacturing. A lot of people have talked about, and we've had lectures while we're here on kind of why semiconductors are important, but I haven't heard anyone yet talk about kind of how they're actually made. So that's what I'm going to try to go over today. Just as the beginning, 对不起，但是我的中文不好，所以我不知道很多相关词汇，因而我要说英文。Quick disclaimer though, I am a high school student. I have not had years of training. I've done my best. I've read a lot of papers. However, there might be inaccuracies. Very sorry if there are. Basically, there's a 6-step process that we're going to be going through today. I'm going to skip the level of actually making the silicon wafer itself because that's too long and I can't be bothered. So first off though, why do we use silicon? Why silicon? There's a scale of conductivity. If you were one of the 4 people who paid attention in your high school chemistry class, you'll remember that rubber is an insulator, copper is a conductor. Silicon falls right in the middle, which makes it really bad at both. But why does this matter? We can change it. So this is elemental silicon. It's 14 protons, 14 neutrons, 14 electrons. It forms a chain like this. Now, but what we can do here is we can switch out one of the silicon atoms, if we can magically replace it, which we'll get to later, with a phosphorus atom. The way electricity works is it wants these free electrons, and the more free electrons there are, the easier it goes from one side to the other. It conducts. So by putting in a phosphorus atom, we suddenly have a free electron because all the other electrons are bonded. If we do that a bunch of times, we have a lot of free electrons, so it becomes more conductive. So our original might not conduct, but once we change out some of these, it'll start to conduct. Everyone following along so far? All right. So then what we can do is just change them in some areas, and then suddenly it'll only conduct path through what we've done. All right? We can also replace this with boron atoms to do the opposite and make it so electricity doesn't want to go to that area. So step 2, we're assuming we have our silicon wafers. We need to grow an oxide layer. But what is an oxide layer? We unfortunately cannot directly change the atoms like this. We don't have tweezers, we can just go pluck out one of them. So what we can do is we can change our trait, an oxide layer is how we prevent certain areas of the silicon from being changed. Basically, it's a thin layer of oxygen that we can carve our traces into. Anywhere on the chip this layer is, the change won't happen. So it's kind of an inverse mask, if that makes sense. It also allows us to stack traces together because we can do it in multiple dimensions. This is how modern semiconductors work, but we're not going to go into that because it's very complicated. There's 2 types of oxide layer formations. There's the dry thermal method, which has the benefit of being very high quality, but it's slow and has very thin layers of oxygen. Because it's similar to rust, where metal's always rusting, but it sometimes happens really fast. So all we're doing is we're putting this in a furnace and making it happen way faster. There's also wet thermal. Dry thermal is we're just putting it in a furnace with no added anything. Wet thermal is we're also adding in water to give it more oxygen that it can then pull apart because of the steam. Wet thermal has the downside of being lower quality, so the layers might be more uneven, but it's fast and gives really thick layers. So that's why some industries use it. Traditionally, industry uses the wet method to clean their wafers along with some other chemicals, and then uses the dry method to grow the kind of final oxide layers that these traces are made in. This is what oxide layers actually look like when they're grown on silicon. The different changes in colors that are really pretty correspond to how physically thick the oxide is. So oxide growth in industry is unfortunately slightly more complicated than just putting it in a furnace. Every company, this is going to be a trend where every company does not want to share their information at all, but most use some sort of chemical vapor deposition, which is a really fancy way of saying they use some chemicals, they kind of throw it in a furnace and go, yeah. Basically, yeah, in general, it's silicon that we put in a furnace and heat it up a lot so that oxygen bonds quicker. So here's our oxide layer on top of our silicon wafer. And if we bring in our magical atom replacer, we find that it's now protected. Yay! Problem is that we want part of this to be changed because we do need to alter some of it so that part of the area can be made conductive. So how do we do that? We need another layer called photoresist and photolithography. Yay! we're going to add another layer on top. This is called photoresist. It's kind of like a glue. Have anyone ever played with those like glow-in-the-dark t-shirts or like the UV-activated paints? It's very similar to that. Anywhere we hit this photoresist with a like UV flashlight, basically, it will then uncure. So we paint it on, let it dry. We hit it with a UV flashlight. Wherever we hit it with that UV flashlight, it will then uncure our photoresist, or if we bring in our laser and uncure it, that section then becomes that, so we can come in and dissolve it with acid, and it only dissolves in that one area. We're still following? All right, I'm speaking very quick, I'm sorry. So if we bring back in our atom replacer, we then can make that one section of silicon conductive. All right? So what exactly is this photoresist compound? We don't exactly know. Suppliers won't say. It has a polymer resin, which is basically, if you've ever used two-part resin, that's one of the substances. It kind of forms the base. It's a photoactive compound, so that's the thing that actually makes it so that when you hit it with the laser, it uncures, and then some sort of solvent that makes it a liquid so you can paint it on. If you would like to know more, feel free to contact one of these companies, as they are who makes it. These are some of the main suppliers for TSMC, as far as I can tell. So how it is used in manufacturing. We have our wafer. We have our wafer oven. We're going to throw it in the oven. Give it a second. It comes back out with our oxide layer. Pretend there's a photoresist layer as well. I forgot to put it on. And then as it grows the oxide layer, now let's say this circuit is the pattern we want to put on our semiconductor. We take the inverse because we need the mask, remember, because anything that gets hit with the light, we put it on. Hits with the light. Now all of this has been made so that we can then dissolve it. So it makes so we can dissolve it. Sounds easy, right? It actually is. At this scale, at least. The problem is that we're running into in the semiconductor industry is things that get made small are really hard. So the problem is actually doing it smaller. To get it smaller, we cheat. We don't need to make the mass smaller, though. We just focus the light, because making things big is easy, and then focusing the light down is a lot easier. Here's the Taipei image that most of us have used in our PowerPoint. You've all used binoculars before. But what if we flip those binoculars around? It gets smaller. So basically what we're doing is we're taking our mask, we're taking a microscope objective, and we're using it backwards from how it's intentionally designed to be used. Bring in our laser, shine it through, it gets way smaller. All right? So photolithography in industry, ASML basically does it. It's really complicated. They use tin and lasers. I'm not going to explain that, but it uses the same principles that we've discussed here. Etching. New problems. If we just drop acid onto our photoresist layer, we'll get an uneven etch. I showed it earlier, but didn't highlight it. If we bring in our magnifying glass, we can see there's a little overhang here. This is a problem with wet or isotropic etching. It basically will go in and dissolve more than you want, because the fluid will flow, right? So that's where dry etching comes in, which is what the industry uses. The industry explanation, no public information at all. We can look at the chemicals they use to try to gain an understanding, because they use gases instead. Here's a commonly quoted list from SK Hynix. If we take that, cross-reference it with some other things, it's mostly fluorocarbons, which I think they're mostly using because of the source of fluorine is a good etchant. And then we can kind of see, though, that they've been mostly phasing that out in favor of nitrogen trifluoride. It's a pain. Basically what they're doing is they have this big fancy etchant machine. They throw their wafer in. It does some magic. It comes out fully etched. Step 5, ion implantation. Remember this from earlier where we changed out our phosphorus atoms? Yep. There's no atom replacer. It's not a real thing. I'm sorry. This is from NTU. If we translate it, still makes no sense. So here's this ion implanter. It's basically a cannon. Here's our cannon. We take some phosphorus, load it in. It does a thing, and then it shoots it right at our thing. What this is doing on a chemical layer is it's taking our phosphorus atoms and shooting it really far into it, and then they're bouncing off and getting wedged in. Here's the DAP for how that does it. Some of them kind of go a little funny, and then if you want to do this is from a PhD dissertation. You're all welcome to read if you'd like. Or various different things. Step 6, we're almost done. Packaging. We just need to make it so the wafer can be used. We got to cut it into a lot of pieces. I'm only going to go over the easiest and most common form because I'm almost out of time. I stole this video because I ran out of time. We cut it with a bunch of diamond discs. It drops out. We then have a bunch of chips. And then it's ran into wires, and then that So, a quick overview. We take our wafer, we grow an oxide layer. This then gets painted with photoresist. We bring in our circuit mask. We take the inverse, we shrink that down, tile it a bunch of times, bring it up top, take our thing to focus it down with, bring some light in, paint it on, etch it down. Now we've got our etch thing. We come in, we take it, we dope our area. And then that we've doped it, we can cut it. Oh, sorry. I spent way too long on this to not show it. So then that we've got our individual circuit, we bring it in our little IC package, bring it over, hook it up with some wires, give it, and label it with a name. Here are my academic sources. Here are my photo credits. Thank you very much.